Number 1, without calculation, check if each of the following matrices is diagonalizable. So in this question we got a 3 by 3 and lower triangular matrix. Okay, because we got all 0 there. And when we have a lower triangular or upper triangular matrix, then the eigenvalues are what? Just the diagonal elements, 2, 4 and -1. So 3 by 3 matrix, we got 3 distinct eigenvalues. Then by a theorem, this is yes, this matrix is diagonalizable. Second question is a 2 by 2. Oh, this is already a diagonal matrix. Trivial question. So yes, number 2. A is a 5 by 5 matrix with 2 eigenvalues. One eigenspace, let's say 2 eigenvalues, so lambda 1, lambda 2. So it's a 5 by 5. For A to be diagonalizable, we have to have 5 linearly independent eigenvectors. Let's see what it says. One eigenspace is 3-dimensional. Let's say for this one, 3-dimensional means we get 3 eigenvectors. And the other eigenspace from this one, let's see, from this eigenvalue is 2-dimensional. So we get 2 eigenvectors. So V3, say V4, V5. Is A diagonalizable? Yes, because these vectors will be always linearly independent. A is 5 by 5 matrix and we got 5 many linearly independent eigenvectors. That's why A is diagonalizable. Yes, that's by a theorem. Because we have 5 linearly independent eigenvectors. A is a 3 by 3 matrix with 2 eigenvalues. Let's say lambda 1, lambda 2. In fact, what happens is when we count multiplicities, we have 3 eigenvalues but 2 distinct. Same thing here. For 5 by 5, counting multiplicities, there are 5 eigenvalues but 2 eigenvalues means 2 distinct eigenvalues. Each eigenspace is 1-dimensional. That means from lambda 1 we get 1 vector. From lambda 2 we get another 1 vector because 1-dimensional eigenspace. Is A diagonalizable? Let's check. So it's a 3 by 3, so we need 3 linearly independent eigenvectors. But how many linearly eigenvectors are here? Only 2. So no. Only 2 linearly independent eigenvectors. While we need 3 for A to be diagonalizable by a theorem. Number 4. A is a 4 by 4 matrix with 3 eigenvalues. So lambda 1, lambda 2, lambda 3. One eigenspace is 1-dimensional. Let's say from this one, 1-dimensional means we get 1 basis vector. And one of the other eigenspaces is 2-dimensional. One of the other eigenspaces is 2-dimensional. I don't know from which one. Let's say from this one, it's a 2-dimensional. Okay, this is 1-dimensional, this is 2-dimensional. So we get 2 vectors. And it does not say one of them is 2-dimensional. So obviously this is 1-dimensional. So let's say V1, this is V2, V3, V4. We can go in this way. Okay. One of them is 2-dimensional. That means how many linearly independent vectors we have here? We got 4. It's a 4 by 4. Is it possible that A is non-diagonalizable? No. A is diagonalizable since there are 4 linearly independent eigenvectors. Okay. Number 5. construct a 2 by 2 matrix that is invertible. Means when we write 2 by 2, the determinant should be non-zero. Invertible but not diagonalizable. Okay, so let's try. Not diagonalizable means if the eigenspace is one dimensional or only one eigenvector. We can take 1 1 and put any number here, let's say 2 and 0 or 2 0. So if I take this 2 by 2 matrix, this is invertible, right? Because what is the determinant of this matrix? This is 1 minus 0, 1. Determinant is non-zero, means invertible. Now how can we say this is not diagonalizable? So from this one, what are the eigenvalues? 1 1, just 1 with multiplicity 2. Now we can find the corresponding eigenvectors. If we find two eigenvectors, linearly eigenvectors, then this will be diagonalizable. But unfortunately for this type of, when I construct in this way, if we find eigenvector, if we try to find eigenvector, there will be only one. That means not enough eigenvectors for this matrix to be diagonalizable. So this one would work. So you can check, in fact, lambda I minus a v equals 0 or x equals 0. This is a. If we find eigenvector, there will be only one. So lambda is 1. So 1i means just 1 0 0 1 minus a is just 1 2 0 1. Okay, that v equals 0. If you subtract, you're gonna get 1 minus 1 0. So what I'm trying to say, we will get only one eigenvector. So not enough eigenvectors for a to be diagonalizable. So 1 minus 1 0. This is negative 2. This is 0 0. Now I'm writing just the augmented matrix. Okay, so I don't have to write v anymore. So if you solve this, so this is free variable from this one is free for v, let's say v1 v2, so no pivot, so free. Here's a pivot, so negative 2 v2 is 0. So we get the vector v1 free, we can take 1, and v2 is 0. So we get only one linearly independent eigenvector. It could be 1 0, in fact v1 0 or 2 0 3 0. So this example works. This is invertible but not diagonalizable. In fact, you can write any, let's say a where a is not 0, any number b there. Okay, any non-zero number. If you write this or b here and 0 there, then this works for 5. So we took 1 2 1 0. Number 6, construct a non-diagonal 2 by 2 matrix. Non-diagonal, that is diagonalizable but not invertible. So we want determinant to be 0. So determinant 0 means this way minus this way 0. How about if we write 0 0, then any number here, let's say 1 1. So this is not a diagonal matrix. It's a non-diagonal, obviously. That is diagonalizable. This is diagonalizable but not invertible. Yeah, this part is clear, because if we try to find determinant, that's 0, because 0 minus 0. Is it diagonalizable? So how can we check that? So let's find eigenvalues first, because we don't know the eigenvalues unlike this one. Let's find the eigenvalues, and we know that Whenever 1 1, maybe we get the same. Okay, let's see 1 1, maybe, and then we'll change maybe 1 2. If we get two distinct eigenvalues, we are all set. Okay, when we have a 2 by 2 matrix with two distinct eigenvalues, then that's always diagonalizable. So we want diagonalizable. Let's find the eigenvalues. So lambda I minus a, determinant of that equals 0, characteristic equation. So lambda I means lambda 0 0 lambda, that's lambda I minus a is just 1 1 0 0, and we find its determinant and we set 0. So lambda minus 1 0 minus 1 0 minus 0 lambda minus 0. So I'm writing this bar for determinant equals 0. So let's find the determinant. We multiply this way, lambda minus 1 times lambda, so lambda times lambda minus 1 minus this way, this is 0, minus 0 doesn't count. So from this, how many eigenvectors we get? Either lambda 0, lambda minus 1 equals 0, so lambda equals 1. So we got two distinct eigenvalues. Then by a theorem, when we have a 2 by 2 matrix with two distinct eigenvalues, this is diagonalizable. So this example works for number 6.